Thank you very much. Thank you, Camilla, for the introduction, and thanks for the invitation to come and speak as part of this seminar series. I'm slightly nervous, more so than normal, given the other speakers in this series, but hopefully there'll be something of interest to you in the next hour or so. I'm going to be talking about some work which not by coincidence involves Camilla, actually, the host for today's um, talk and the series. And so this is joint work which we did in a project over the last few years with Camilla and also Rhiann Daniel, who's at Cardiff in Wales, two of my colleagues, Emily and Ruth at the London School of Hygiene and Tropical Medicine, and also Eric van Svet from Leiden. Okay, so I'm going to start off with a few slides just to sort of motivate how we got into this project and what I'm going to be talking about. So the motivation is that we're interested in many situations in trying to estimate the effects of some exposure or treatments which can vary over time within individuals in terms of which treatment they receive. And in the particular situation that we were working on, we were looking at the analysis of randomized trials in diabetes in particular, where patients may, in addition to their randomized treatment, be given some so-called rescue treatment if their diabetes becomes uncontrolled, or they may discontinue randomized treatment. And so the treatments, the randomized treatment, the rescue treatment received by patients varied over time in these trials. And in this sort of context, you might be interested in estimating some sort of treatment effect that differs from what a traditional intention to treat type analysis would be estimating. So, for example, we may be interested in estimating the effects of randomized treatment, A versus B, in a hypothetical scenario where patients remained on those randomized treatments throughout the follow-up period without having any rescue treatment. So no discontinuation and no rescue treatment. But of course, the method I'll be talking about today, G-formula, is traditionally more often being used in the analysis of observational studies where there's no randomization at all. And we're interested in the effects of treatment strategies for some varying, potentially time-varying treatment or exposure. And in that sort of situation, what we had to do is worry about confounding if the treatments are not randomized. So in the randomized trial setting that I was talking about a moment ago from diabetes, the initial treatment was randomly assigned, but the rescue treatment and the discontinuation of randomized treatment was not being randomized. This was something happening due to a combination of physician decisions and patient level decisions. And so we have to worry about confounding, and not just baseline confounding, but time varying confounding, variables that affect what treatment somebody has over time and also the final outcome of interest. And to estimate effects of treatments in this sort of situation requires use of so-called G methods, which were developed by Jamie Robbins and colleagues over a number of years. I'm going to be talking specifically about the method of G-formula, which is sometimes called G computation. And the sort of overarching, if you like, context for this talk is we wanted to apply this G-formula method to a data set where there were missing values. And there's often missing values in data sets, as I'm sure you're all well familiar with. And so the question was, how can we handle missing values in the context of applying this method G-formula for estimating the effects of a time-varying treatment? Okay, so I'm just going to briefly introduce this setting, which or setup rather, of a time-varying treatment and time-varying confounder, which I'm sure many of you are already familiar with. So this is the sort of, if you like, the standard time-varying treatment confounder setup. I've got a treatment or exposure AK, which is the treatment or exposure level at visit K for a given individual. And in general, we could have a baseline 0 up to a final visit capital K. And then we've got confounders measured at visit K, L subscript K, and then a final outcome of interest Y. And this is just, if you like, the sort of standard DAG where at each time the treatment can depend on past values of treatment. So A1 here could be affected by the previous treatment A0 and also be affected by the earlier values of these time-varying confounders L. And then we have a final outcome Y, which could be influenced by all of the preceding variables. Okay, so to define causal effects, I'm going to use potential outcomes. So here, with this simple setup where I just had three different times at which treatment could be varied, I've got a potential outcome y superscript A0, A1, A2, which is the outcome that a given individual would experience if their treatments were set to values A0, A1, and A2 at each of these three time points. So these three letters are just placeholders for specific values of interest. So for example, if I have a binary treatment, Y111 just means what the outcome would be for that given individual if they were treated at each of the three time points. So causal estimands are then contrasts of aspects of distributions of these potential outcomes for different possible values of these treatment sequences A bar. So the bar here denotes a history over time of treatment. So for example, we could be interested in the average outcome if everyone were treated at all three time points, which is this first part of the expression, minus the average outcome across the population if people were not treated at any of the three time points. There's assumptions necessary in order to estimate such causal effects from observational data: consistency, conditional exchangeability, positivity. I'm not going to go into any detail on those. These are the standard identification assumptions in this time-varying treatment confounding setup, but we're relying on those assumptions as we usually would. Okay, so let's go on to say a little bit about what G-formula does, and then we'll go on to see how we can apply G-formula when some values are missing in the data set which we have to analyze. So estimation of causal contrasts in the context of G-formula is based on this formula here, which, given those preceding identification assumptions, you can show that the expected value of the outcome under a given treatment sequence of interest can be expressed in terms of this nested integral. So here we've got the expected outcome given the treatment values of interest, the sequence of values, for example, 0, 0, 0, the confounders at the earlier time points, and here we've got the conditional distribution of each of the time-varying confounders given the earlier values. So to implement this, we have to specify models for each of the conditional distributions involved in this expression. So first, the distribution of the baseline confounders, then the distribution of the confounders at the next visit, given the earlier treatment and the baseline confounders, and then moving forwards in time. In fact, in typical implementations of G-formula, you don't actually specify a parametric distribution for the baseline confounders, but instead empirically average across the distribution of the baseline confounders in the sample. So you don't actually specify a model for it. And similarly, if we're interested, as we often are, in the expected outcome, the mean outcome, then rather than specifying the complete distribution of the outcome given all of the previous variables, all we need is a model for this conditional expectation here. In the way that I presented G-formula here, we're specifying separate models for each of the time-varying confounders given the past. In fact, in common implementations, for example, the G-formula package in R, what they instead do is set up the data in so-called long form and fit pooled models for each of the time-varying variables over time to reduce the number of models required to be fit and to help overcome issues of sparsity. So the integrals in this expression at the top here are generally analytically intractable. And so traditionally, the way that G-formula has been implemented is to use simulation or Monte Carlo integration. So what that means is that we fit each of the models that were on the previous slide and simulate from them under the given treatment sequence of interest. So we simulate baseline confounders, then simulate the confounders at the next treatment, the next time point, imagining that people had a baseline treatment set to the value little a0 that we're interested in, then simulate the confounders at the next visit, and then finally simulate the outcome at the final visit. So then the final step is just to empirically average those simulated outcomes across the individuals, and that is an estimate of the potential mean outcome in the population under that given treatment sequence of interest. So that's how you obtain an estimate of the mean outcome under that given sequence of treatments. In terms of standard errors and confidence intervals, inference for G-formula estimators has traditionally been based on non-parametric bootstrapping. So that means resampling the original data a number of times, capital B here, to each of those bootstrap samples, obtaining a G-formula estimate of the potential outcome mean of interest, and then using the standard rules for bootstrapping, for example, to form a bootstrap standard error, you calculate the standard deviation of the estimates across the bootstrap samples, or alternatively use the distribution of the bootstrap estimates to form confidence intervals, for example, percentile-based bootstrap confidence intervals. Okay, so at the start, I said the problem we were trying to investigate was how to apply G-formula when some data are missing in the original data set. Now, two implementations of G-formula in software are the Stata implementation G-formula, which was written by our colleague Rhian Daniel, and that imputes any missing values once stochastically from models, whereas the G-formula package in R fits each of the models for the time-variant confounders using the complete cases, so the individuals who have each of the variables involved in those models for the time-variant confounders complete. And I'll come back at the end to say a little bit more about what assumptions might be sensible to make when handling missing data in this context of applying G-formula. But for now, what I'm going to say is let's explore how we can apply multiple imputation to impute the missing data when we want to apply G-formula for estimation of causal effects. Well, the most obvious thing to do would be to use multiple imputation to impute the missing data. And so without going into too many of the details for the moment, that involves creating plausible values of the missing values based on models traditionally, and creating a number of imputed data sets, and then applying your estimation procedure, which in this case is G-formula, to each of those imputed data sets. What you get from that is an estimate of your causal effect of interest from each of the M data sets. And what you also need is a standard error from each of those analyses. And then those estimates and standard errors are combined using these relatively simple rules developed by Rubin when he developed multiple imputation. Now, typically when we use multiple imputation, our estimation procedure can give us an analytical standard error estimate, which is easy to calculate. But if in situations like this, where we're using bootstrapping to estimate the standard error, one approach is to use bootstrapping within each of these capital M imputation analyses. So rather than having to use bootstrap sampling, say 1,000 times to estimate a standard error, we're now having to use bootstrapping with 1,000, say, bootstraps in each of these capital M data sets. And so the overall procedure of having bootstrapping nested within multiple imputations can obviously get quite computationally costly. And so what we were playing about with is, can we find an alternative approach which avoids bootstrapping and therefore doesn't have such a high computational cost? And for people like me who don't know much really about causal inference, but know slightly more about things like missing data and multiple imputation, when I looked at how G-formula worked, I sort of thought, well, it's sort of single stochastic imputation of this longitudinal history of confounders and outcomes under the treatment regime of interest. And so that's how I sort of viewed the G-formula, or the implementation of G-formula by Monte Carlo integration. Actually, I talked earlier about simulating an outcome for each individual in the sample under the treatment sequence of interest. But implementations of G-formula typically, to reduce the simulation error or Monte Carlo error, they often create effectively multiple simulated sequences of confounders and outcomes for each individual in the original data set, and then average those across the individuals. So it's getting quite similar to what multiple imputation is doing. And so these sort of close links between multiple imputation for missing data and G-formula for causal inference sort of begs the question, can we somehow use Rubin's combination rules from multiple imputation rather than relying on bootstrapping for inference? And what I'm going to talk about next is basically how we sort of showed that you could do that, exploiting some earlier work on using multiple imputation for generating synthetic data sets. So just a little bit more on the links between causal inference and multiple imputation and G-formula. There's a really nice paper here by Daniel Westreich and colleagues, reference A, which was sort of already pointing to some of the close connections between G-formula and multiple imputation. So here I've just got a little toy data set with a baseline confounder, just a treatment or exposure at one time point, so a much simpler setting, and then an outcome Y measured sometime afterwards. And what we've done here, normally you would just have in your data set the outcome variable Y, but what we've done here, and as they did in the paper by Westreich et al., is to say, well, for the people who don't receive treatment, the outcome that we observe is the potential or counterfactual outcome Y superscript 0. And for those individuals, the outcome under treatment is missing, as denoted here by NA, whereas those who actually were treated, the potential outcomes under no treatment are missing, the ones under treatment are observed. And so this sort of toy example makes quite clear that, and I'm by no means the first person to point this out, that the causal inference problem is in some senses a missing data problem at heart. If we knew what the outcome for an individual would have been under the alternative treatment, we could calculate the individual level treatment effect. So if you view the causal inference problem from a missing data perspective, you might think, well, if I impute these missing counterfactual outcomes under no treatment for the people who actually were treated and vice versa for the ones who weren't treated, I could then calculate the difference in means, for example, between these two columns and estimate the causal effect of treatment. And in this nice paper, they sort of pointed out that you couldn't use Rubin's variance estimator directly here because you've got the same individuals contributing to both the treated and the untreated. So there were earlier connections to the idea of G-formula and multiple imputation that we in this work were sort of building on. So in the preceding slide, the actual observed outcome for each individual was retained in that approach. Whereas in the longitudinal setting in G-formula I described earlier on, you use the observed data to obviously fit the models, but then you simulate completely new sequences of confounder values and outcomes for each individual. So you don't actually retain in the final analysis in G-formula the original data, the original confounders and outcomes. Those are just used in fitting the models, which are then used to simulate data. And indeed, in the longitudinal setting, it may be that actually no individuals in the observed data set followed the particular treatment regime or sequence that you're interested in. So what we're going to do now is just talk about how we can use multiple imputation to implement a version of G-formula, exploiting these earlier results where people were using MI to generate synthetic data sets. Okay, so this is the basic idea then. If we're interested in estimating the mean of the potential outcomes under a particular treatment sequence, A bar, what we do is we take the observed data and augment that observed data set by some additional rows. And here I'm using n sin just to denote the number of additional rows we add to the data set. In those additional rows that we add, we set the confounders and the outcome to missing, and we set the treatment variables to the value that we're interested in, A bar here, the lowercase a bar. So whatever treatment sequence we're interested in, we set in these additional rows the treatment variables to those specified values. We then run our multiple imputation software on this augmented data set, generating M imputations. And so what that's going to do is fit models to the observed part of the data at the top and use those fitted models to impute the missing values that we've artificially created in these new rows that we've added onto the data set. And then we can sort of carry on, at least in terms of point estimation, in the normal way that we would for multiple imputation. So average the estimates of those simulated outcomes in each of the data sets, and then average those averages across the capital M imputations. So here is what the data set would sort of look like. I've got in the top half my observed data. I've got a very simple setup here with just one confounder at each time point, so L0, L1, L2, and then I've got a binary treatment, A0, A1, A2, and then a final outcome, Y. I've created a new variable, R, just to denote whether the row is an originally observed row, R equals 1, or one of these artificial or synthetic rows R equals 0. And so as I described on the previous slide, I set the confounders and the outcomes to missing in these new rows, and the treatment variables I've set to the value of treatment that I'm interested in, which for an example here, I've set to 1, 1, 1. So this is going to enable me to estimate the mean outcome if individuals were treated at each of the 3 time points. So how do we do the imputation? Well, you've got sort of an artificial missingness structure, a block monotone missingness structure. And what we can do then is impute the baseline confounders L0 and then impute the visit 1 confounders given the baseline treatment and the baseline confounders, and impute forwards in time using whatever models we deem appropriate for the time varying confounders and then the outcome. And so what this means is that you can sort of make use of existing multiple imputation software. So for example, the mice package in R that many of you might be familiar with. And normally in the mice package for doing multiple imputation for missing data, when there's a complex pattern of missingness, you might have to, in general, iterate around the conditional models that it uses a number of times in a sort of Gibbs sampler approach. In this particular situation, at least where we didn't have any missing data to start with, no such iteration is needed. So you can set the sort of iteration number of iterations to perform just to 1 in the mice software if you were using that, for example. I've just talked about how to estimate a mean of potential outcomes under one sequence of treatment. Of course, a causal effect is something about a contrast of outcomes under 2 different treatment sequences. And so what we typically are interested in, oh, I seem to have lost my y's here. There should be a y there and a y there. I'm interested in the mean outcome under treatment sequence 1 minus the mean outcome under treatment sequence 2. And so to do that with imputation, we simply add even more rows and set in those in that second batch of rows the treatment variables to the second sequence of interest, A2 bar. And then in the imputed data sets, we're then calculating a difference in means between those individuals who were assigned to the first treatment sequence minus the mean of those individuals assigned to receive the second treatment sequence. So obtaining the sort of point estimator is relatively simple here. How about estimating the standard error? Because this was sort of part of a motivation to try and avoid the need to use bootstrapping. Well, ordinarily with multiple imputation, you use these very simple combination rules developed by Rubin. And what they involve is estimating the standard error or variance of your point estimator in each of the imputed data sets. So they're the within imputation variances, and you average those to give what I'm denoting here, V hat, the average within imputation variance. You then estimate the between imputation variance, which is just the sample variance of your point estimates across the capital M imputed data sets. And then you combine these, which aside from an adjustment for the fact that you've done a finite number of imputations, which introduces some Monte Carlo error, it's essentially the between imputation variance plus the within imputation variance. So it's very simple, and part of the fact that it is so simple is, I think, part of the reason why multiple imputation has been such a popular approach for handling missing data. Unfortunately, if you apply this formula to this G-formula imputation approach that I've just described, it doesn't work. The variance estimator here gives a much larger value than the true repeated sampling variance of the point estimator. And this bias in Rubin's variance estimator is due to a form of so-called uncongeniality. And in this particular case, it's that the imputation model and the analysis model are being fitted to different portions of this augmented data set. So there's various assumptions underlying the justification for Rubin's variance formula, and essentially those conditions don't hold in this particular example. So how then can we rescue the situation? Well, within the survey sampling literature, there's quite an established sort of field within it looking at how you can use multiple imputation to impute either some of the variables or maybe all of the variables to create so-called synthetic data sets. And the motivation in this field, in this area of that idea, is that if you want to release survey data sets to analysts, but you may be concerned about confidentiality, rather than releasing the actual data sets to analysts, you could release either a fully synthetic version of the data or a partially synthetic version. And so the idea here then is to use multiple imputation, which was originally devised for handling missing data, to impute or simulate variables or values of variables for new or synthetic individuals in the case of this fully synthetic idea, to avoid releasing their actual original data sets, data values to analysts. And in this context of using MI for synthetic data set generation, in a nice paper, Raghunathan, Reiter, and Rubin showed that you could modify Rubin's original variance formula and modify it in a very simple way, which is to switch the previous expression had a plus here to a minus. So rather than the between imputation variance being added to the within imputation variance V, we do the between minus the within. So they sort of looked at that in the context of synthetic MI, and in our paper we used some of the theory that Jamie Robbins and Wang developed at the end of the 1990s for the sort of frequentist properties of multiple imputation and Rubin's original variance estimator to show that this variance estimator is asymptotically unbiased for the G formula via MI approach that I've described earlier. Okay, so I'm going to briefly talk about some of the simulations. I'm not going to go into lots of details. There'll be a reference in the slides at the end to the paper where more details given. But basically, we performed some simulations with 500 individuals, 10,000 simulations per scenario, a very simple setup with two intermediate follow-ups and a final outcome Y. We then imputed the confounders and the outcomes using the mice package. So here are the models. I'm not going to talk them through. Fairly standard, simple models. And we were looking at the causal effect of the mean outcome if you always treat, minus the mean outcome if you never treat. And under the data generating mechanisms that we have here on the slide, the true value of that causal effect is 3. So one difficulty with this modified variance estimator is that it's possible for this between imputation variance B to be bigger than the within imputation variance V, and so the variance estimator can be negative due to the noise in this between imputation variance estimator. And there's various sort of practical things you can try and do in response to that. What we did in our paper is to try different values of the number of imputations, so 5, 10, 25, 50, 100. And then we evaluated the performance of a fairly pragmatic solution to this problem, which was that if we obtained in one of the simulations a negative value of this variance estimator, we added another batch of imputations and did that again if necessary until the variance estimator became non-negative. So this table is showing the results of these simulations for different numbers of initial imputations, 5 up to 100. And the confidence interval coverage here is getting better as you increase the number of imputations. I'm now not sure. There's a correction to the degrees of freedom in the confidence interval, and I'm now not sure which one I'm showing there. Apologies. There's a modified degrees of freedom formula proposed by Raghunathan and colleagues in that original paper, which basically improves the coverage performance. But even with 25 imputations, the coverage is looking pretty good. And although we started here with 25 initial imputations, the maximum we ever needed to get a non-negative variance estimate was 50, so adding an additional 25 imputations. And once we got to 50 imputations, we never needed to add any more to obtain a non-negative variance estimate. So basically, in an admittedly simple simulation setup, this variance formula developed for the synthetic dataset creation setup seems to work quite nicely for G formula. So so far then, this method works quite nicely. You can implement this using existing multiple imputation software for missing data. You obviously have to fiddle around a little bit because you have to add these artificial rows to your data set, artificially set the variables to be missing except for the treatment variables. And then you also have to modify the variance formula. So it's not too tricky. But we've got a little package in RG Formula MI just to facilitate this method to help you do it, which links in with the mice imputation package to do the actual imputation of the confounders and the outcome. Okay, so that was sort of how you can use multiple imputation software and this modified variance formula to do G formula using imputation, multiple imputation type approach. But the original situation that I was talking about was a situation where there were missing values in the original data set. So how can we adapt this to the problem where in the first place we've got some missing values, missing actual values, as opposed to missing potential outcomes? So the answer is it's pretty straightforward. If we've got a data set with some missing values, we're going to use multiple imputation to impute those missing values and then also impute these missing values in the potential outcomes of these augmented rows in the data set. And there's at least two approaches that you could adopt here. So you could impute the missing actual data, so the missing values in your original data set, and the missing values in these augmented rows in sort of one go. Or you could impute the missing actual values first and then impute the missing potential outcomes conditional on those imputations of the missing values. And for arguments that we elaborate on in the paper, we think that option two is more attractive because assuming that the amount of missing data in the original data set is relatively small, then we just have to impute that small amount of missingness to create this a so-called monotone missingness pattern. And then at the second stage, you don't have to repeatedly iterate around these models as you do in general when you have a non-monotone pattern of missingness. And this sort of approach to handling imputation of missing data when you've got a combination of monotone missingness and intermittent missingness is quite well established in the missingness context. Okay, so I'm just going to briefly step through some simulation results in the context of having some missing data as well. So we had the same setup as before. We made data missing in each of the variables with a probability p that we varied. These are the marginal probabilities that values in each of the variables were missing. So actually, the 0.5 means that there's a 0.5 probability of each of the variables involved being missing. So that's really quite an extreme scenario. So these are the simulation results and showed that basically, again, this Raghunathan synthetic MI variance estimator works very nicely in terms of the average of it getting close to the empirical standard error of the estimates. And confidence intervals had really quite nice coverage. So it really seems to perform quite nicely so far in simulations. Okay, so I said at the start that you could use bootstrapping with G formula, but the one of the issues with that could be that it would be very time consuming. If you're using, say, 1,000 or more bootstrap samples, and let's say you want to use 25 imputations for missing data, it could be pretty time consuming computationally. So I'm just going to talk through a little bit of a illustrative example that we report the analyses of in the paper, and included in that is some timings of run times for this MI approach that I've just been describing, and contrast that with the run times for a bootstrap approach. So the analyses were of data from the UK Cystic Fibrosis Registry, and this registry collects longitudinal data on almost all the people with cystic fibrosis in the United Kingdom. The individuals in the registry have annual clinic visits collecting clinical status, lung function, medications that they're receiving, hospital admission data, and health complications. And in the analyses that I'll briefly show you here, we use data from 4,759 individuals who had been on this treatment called DNase for at least 2 consecutive years. And the question we were trying to use the data to answer was that for such patients who'd been on that treatment for at least 2 consecutive years, does adding hypertonic saline treatment improve their lung function as measured by FEV? So we looked at the FEV outcome not just at some final time point, but also intermediate time points. So at years 1, 2, 3, 4, and 5, post our baseline visit. And we've got two treatment sequences of interest here. The remain on the DNase treatment, or in addition to DNase, take the hypertonic saline treatment in addition. Baseline confounders consisted of sex, CFTR genotype, ethnicity, date of birth, rate of FEV decline in the year preceding baseline. And then we had time variant confounders of earlier FEV measurements, their history of respiratory infection, IV hospital admissions, BMI, pancreatic insufficiency, and use of IV antibiotics. So the missing data here were due to a combination of reasons, partly due to things not being recorded at annual visits, partly due to people not being in the registry due to death, and partly due to administrative end of follow-up. The missingness due to death raises an important question about what the estimand should be, and I don't really have time to talk about it, but further, suffice to say, I don't think there is a simple, good solution to the problem of missingness or the outcomes being ill-defined because of death. But there's obviously an important and emerging literature on that problem, which in this talk I'm essentially going to ignore. So the analyses that we did two different analyses of the data set. So the data had missingness, as I just described, and in our paper there's some further details on how much missingness and which variables were particularly affected. But we wanted to sort of isolate the comparison between G formula without using multiple imputation to a more traditional G formula approach from the situation where there are no missing data to the situation where there are some missing data. So what I'm going to do is show you some results which first are based on the complete cases in the original data, so the individuals who didn't have any missing values. And then some results where we analyze the actual data where we had to handle the missing values. So in the complete case analysis, we used the G formula package in R. We simulated for 100,000 patients and used 1,000 bootstraps to estimate standard errors. And then for the G formula by multiple imputation approach, we used 200 imputations and this many synthetic augmented rows in the data set. So this is the same number as the original sample contained. And then for the analysis of the actual data set where some values were missing, so the larger full sample, but where some values of the variables were missing, we just apply G formula, which by default, as I mentioned earlier, fits each of the models that it fits using those individuals who had all of the variables concerned measured. So at a given fit, that's the conditional distribution of one of the confounders given earlier variables of confounders and treatments. And so all of the long data form records contribute to that if they had each of the respective variables observed. And then the alternative was to use multiple imputation to impute those missing values. So we used the mice package to create 200 imputations and then applied this G formula imputation approach to impute the artificially missing potential outcomes or counterfactuals under each of these two treatment sequences of interest. So here are the results. On the top half are the complete case results, on the bottom half are the analysis of the data set with some values missing. And I'm not going to go through all of the results in detail, but we've got the treatment effect here, denoted TE at year 1, 2, 3, 4, and 5. There wasn't anything in terms of statistically significant treatment effects, and this is sort of consistent with previous analyses of this question using this data. But what we were particularly interested in is comparing the point estimates of the treatment effects and the confidence intervals between these two methods. So I'm just going to stop for a moment and so the treatment effect estimates were more different between these two methods than could be due to Monte Carlo error. And that is attributable to the fact that the models that these two approaches were using were different. So here in the G-formula impute approach, we were using the mice package, which sets things up in terms of a separate column for each confounder at each time point and fits models for each of those conditional on the past variables. So if you like non-pooled models, whereas the G-formula package in R is fitting these pooled models in the so-called long data format. And so that is the fundamental difference in terms of the point estimates between these two different approaches. It's not inherent to the sort of imputation versus bootstrapping approach. It's more to do with the way that the packages are and the implementations are choosing to model the distributions required to implement G formula. In terms of the runtime, there was a really dramatic difference in the runtime, so much quicker for the multiple imputation approach, which didn't need any bootstrapping, compared to the G formula one, which used bootstrapping for inference. In terms of the partially analysis of the partially observed data set, we saw similar sorts of differences in terms of the runtime, but the G formula impute approach became much more slower compared to the situation where there was no missing data in the complete cases, because it had to do imputation of the missing data and then it had to do imputation of the missing potential outcomes. But overall, in terms of the runtimes, we were quite surprised by how much quicker the imputation approach was compared to the approach which required the use of bootstrapping. So in terms of the substantive question, there was little evidence that adding hypertonic saline had any effect on FEV1. And as I said, the differences in terms of the point estimates are not really to do with the variance estimation approach differing between these two different routes, but rather the different ways that they're specifying the models involved. The Monte Carlo standard errors from the two approaches were smaller from the imputation approach, just essentially because effectively the point estimate there is based on 200 times 4,759 individuals, whereas the point estimate is based on 100,000 under the settings that we've got here in the G formula package approach. Okay, so just some concluding thoughts then. That we didn't set out to sort of develop a new method here. We sort of ended up coming up with it in the context of trying to apply G formula with multiple imputation to handle missing data. It seems like an attractive approach to implementing G formula. I certainly wouldn't like to say it's the best approach or better than the traditional approach, and so from my perspective, I quite like this piece of work, just in terms of seeing the connections between causal inference and missing data, and the idea of viewing the causal inference problem from a missing data perspective, I think is quite nice, particularly if you are familiar with multiple imputation and similar methods for handling missing data. You can take a look at our preprint for more details of the things I've been talking about. It's going to be published soon in Statistical Methods in Medical Research. There's a package in R implementing it, which sort of links up with the mice package that I've mentioned called G Formula MI. And application of the approach and other methods for this diabetes trial example has just been published in Biometrics, which is reference 4 there. There's various things that I've not talked about, which I should have, and this is my attempt to remedy that to some extent. So one is, what assumption should you make about missing data in the context of doing these sorts of analyses? Well, the complete case type assumption made by the G formula package, I think, may in many cases be more plausible that multiple imputation, at least as usually implemented, relies on. And that's in particular because the complete case type assumption being used here is much easier to define and understand, and therefore judge the plausibility of, than the MAR assumption when there's a complex non-monotone pattern of missingness. Often a large amount of missingness in an observational or study over time is due to dropout or censoring, and you can view that that missingness or censoring as part of the time-varying treatment. This is a reference here to Hanan and Jamie Robbins's book, and there's a nice bit about it there. And you'll see in many of their papers that in the context of a longitudinal study with monotone dropout, that you one way of handling it is to view it as part of the treatment and then say that what you're interested in is estimating potential outcome means under the treatment sequence of interest, which consists of the treatment itself, but also this sort of additional pseudo treatment, which is under the no censoring treatment. Nevertheless, I think there's often going to be sporadic or intermittent missingness as well as dropout that you have to handle one way or the other in analyses of these sorts of data sets. Part of the reason I sort of motivated this was to sort of get past this computational issue with bootstrapping. And in that context, it's important to mention that there's other versions of G-formula, so the so-called iterative conditional expectation approach of G-formula that avoids Monte Carlo simulation integration entirely by fitting models for conditional means and then models sort of iteratively going back in time, regressing those on the earlier values of the confounder and treatment history. And because that approach doesn't involve Monte Carlo simulation, it is possible, as described in this paper reference line here, to estimate the variance of the resulting point estimator using estimating equation theory and not requiring something like bootstrapping. Okay, I'll stop there and I'll just cycle through the references while Camilla, I don't know if there's questions that we want to go through.